Good morning. I don't know if it is on. Well, let's start this singular event. Dear Adam Smith, Chief Scientific Officer of the Nobel Media. Dear Eduardo Recoder, President of the AstraZeneca Foundation. Dear students, dear professors, all of you, welcome. It's my privilege and pleasure as the Dean of this faculty to welcome you here, all of you. We are today, as you know, honored to have May-Britt Moser with us. Prepare yourself to be challenged, excited, and inspired by her words. Dear May-Britt, thank you for coming. And just before I hand over to Adam Smith to make a short introduction of her, I want to say once more, on behalf of the Faculty of Medicine, welcome. It's wonderful to see you here. Thank you.
So good morning, everybody. As Dean Diaz says, my name's Adam Smith from Nobel Media, and on behalf of all at Nobel Media, I'd like to welcome you to this morning's lecture, which, as you see, is part of the Nobel Prize Inspiration Initiative. This is a global collaboration between Nobel Media and AstraZeneca, which takes Nobel laureates around the world to meet audiences of young scientists like all of you. We've been running this for 8 years. We've run 24 events on 5 continents, but we've never been to Complutense before. And so I'd like to thank the Faculty of Medicine at Complutense and Dean Diaz for so beautifully welcoming us and for providing this incredible audience, which is exactly what we want to see. In fact, it's so much exactly what we want to see, I want to take a photograph of you all, and I want to send it back to Stockholm so that they know what this is all about. So, fantastic. Thank you. Now, when we started planning this event, my colleagues in AstraZeneca in Spain said, Spain's an important country and we want to be ambitious for this event. So I know most Nobel laureates are men, but we'd like a woman. And we know that most Nobel laureates are older, but we want a young woman. And we know that most Nobel laureates are not so active in research anymore, but we'd like somebody who's really active in research. And I said, that sounds like May-Britt Moser. But she is really hard to get. I've asked her before to come to things, and she's terribly polite, but she says, no, I'm too busy in the lab. I'm sorry. But there must be something special about Spain, because when I asked her to come to Spain, she said yes. So I think we're very lucky. And I like to think about the initiative as a way of reminding us how exciting science is. We all join science because we love it. And then after a while, we begin to realize that experiments don't always work, and we don't like the lab, and we can't get money. And you begin to lose focus sometimes. So it's very nice to be reminded how special science is. And I cannot imagine anybody better to remind one of that than May-Britt Moser. So I will leave it to her to do that job. And I'd just like you all, please, to welcome May-Britt to the stage. Thank you.
Thank you so much. This is the warmest welcome I've ever got, so I will remember this. And before I start my talk, of course, I would love to say thank you to the organizers, to Adam, who asked me to join, so the Nobel Initiative, AstraZeneca for paying, and for the university here, and for the dean organizing this, and to all of you that you want to spend 1 hour with me and try to understand what we are doing far north. So I hope you get some ideas. So I'm interested, and I hope that when I'm done here, then you have some ideas how memory is encoded in the brain, what is necessary to make memories. And I give you some cues here. Space, time is important. Once upon a time, there was a tiny girl, and she had one mission in her life, and that was to try to understand the world. And it developed into this idea, I want to understand how the brain is generating behavior, memory, our cognition, our emotions. And do you know what happened then? This girl, she was so lucky that she became a scientist. And as a scientist, she was allowed to ask these questions in the lab. And what also happened was that I experienced something that I want to share with you, because it's a way to show you one of my memories. It happened in 2014, and I was sitting in Trondheim. I was talking to the people in the lab. We had an exciting discussion, and then I got a very annoying phone call. And I understood after a while that the message was not annoying. Okay, so this was a memory I wanted to share with you. And what is important here is that this is an example of a very strong episodic memory. And Endel Tulving, in the 70s, he said, if you want to study episodic memory, there are 3 key questions that you have to understand. And if you want to understand how the brain is dealing with this, then you know a bit more about episodic memory. And that is what I hope that we can do today. So there are 3 questions. Where did it happen? When did it happen? And what happened? What we also know is that there is a brain structure just inside here, in the temporal lobe, that is called hippocampus. In fact, there are 2 of them. And it's called hippocampus, as you know, because hippocampus is seahorse, and it looks like a seahorse. So this hippocampus here is dissected out by a professor in Hungary, Laszlo Serres, just to show how similar the hippocampus is to the seahorse. What is important is that even in the 50s, we heard about this structure, because there was one man that you probably have heard about. He was called HM at that time, Henry Molaisen. he had to remove both of his hippocampi because he had epileptic seizures, and the medicine didn't help him. And then they did some experimental surgeries and to remove the hippocampus. He woke up, and he was a very nice guy. So he was social, he was laughing, he looked very normal. And then they started to test him with the IQ tests, and he was better than before because he wasn't disturbed by the seizures. But when people came back, even after 15 minutes, he said, "I've never seen you before." So he couldn't encode new episodic memory. He couldn't even know how to find the bathroom. So he didn't have the where. And he didn't have the time because he didn't know when things had happened and in what sequence. But he could learn other things. He could learn to write from a mirror, and he could learn quite some things, but everything that had to do with episodic memory, even to learn that his uncle had died, he couldn't encode into his brain. So in our lab, we started with where. But before we started with the where question, there is an important man besides my ex-husband, Edvard Moser, and that was my supervisor, John O'Keefe, who we earned the Nobel Prize with. What he did was to ask, there's something special with this hippocampus structure, since it's so important for HM and other patients. If you don't have it, you can't encode episodic memory. So he had then a rat, and he had small sensors close to the cells in the hippocampus. And the rat was just walking around happy. So in his lab, they got rice. In my lab, they got chocolate, of course. So what happened is that he was just studying this rat, running around chasing rice or chocolate. And then he asked himself, if I listen to one hippocampus cell, what is this hippocampal cell reacting to? Can I understand that? And I'm going to play the video, and then you can see yourself, even though I have given you a cue here. So now you hear one single cell that is active. And you see the rat is doing exactly the same thing, chasing chocolate. So what is so special about this corner? We even use this color code to show you that there is something very hot in that corner. This cell is responding to something in that corner. And then could it be that there's a special odor? Could there be some scratch in the floor? What is it? So John and others recorded many cells, and they found out that each cell had its own preference, where to be active and where to be silent. And if you record more than 100 cells at the same time for some time, then you can predict where the animal is with a 5 centimeters precision. That's quite remarkable. So just by listening to the cells of this animal, you know where the animal is with a precision of 5 centimeters. That's scary. So for Edvard and me, it really started when we could have our PhD defense in 1995. So here you see Edvard, and here you see me, our oldest daughter, and our supervisor, Per Andersen, and here we have John O'Keefe. So the link to go to his lab to learn this technique to learn to record from these single cells in the hippocampus. That was quite easy. So at that time, we brought 2 children with us, and we brought this technique to Trondheim. So the first question we had when we explored this was exactly what I asked you about. Why are these cells active, and where is this information coming from? Is it so that the information is processed within the hippocampus itself, or is it fed in from a structure, brain structure, outside the hippocampus? And in order to address that question, we had this fantastic student who took his medical PhD and medical degree at the same time in our lab. And this is a rodent brain. In fact, this is a rabbit brain drawn by my supervisor, Per Andersen. You see, if you lift the cortex, then you see this beautiful structure. It looks like a sausage. But it's beautiful. And if you then slice it, you see these lines of cells here. And the information in hippocampus is coming from entorhinal cortex. It's going through this loop here in dentate, up to C3, and then up to C1, and then back again to entorhinal cortex. So we asked, is it so that if we block this loop in the hippocampus, do you still get play cells? Yes. So here are examples of 7 beautiful play cells, even though we cut this loop in the hippocampus. So what did that tell us? The information that these cells use to generate the play signal has to come from outside. And our best guess, that was entorhinal cortex. So then we took our sensors, our electrodes, and we decided to place these electrodes in the entorhinal cortex. So this is a brain, rat brain, that you see from behind. The cerebellum is removed, and this colorful area here is the entorhinal cortex. The right one, that is the medial entorhinal cortex. And at that time, we collaborated with Menno Witter, who is now in Trondheim, running his own group. And we decided to put our sensor in the most dorsal part of the medial entorhinal cortex. People had been recorded up before, but they had recorded down here and concluded that there's nothing interesting. So now you have to see yourself. I'm going to play another video. There's no sound, but there are some white dots telling. Do you see anything? Or there's some strong light here, so I don't know if you see. You see it? Okay. So you see these white dots? And this is the activity of one single cell in this area in the entorhinal cortex. And you see that it looks not so nice. So maybe these people were right. There's nothing interesting in the dorsal, or in the entorhinal cortex. But if you have a big enough environment and you have really happy animals that love to chase chocolate so that you get enough coverage, you get a pattern that looks like this. So this is in a 150 by 150 box. These black traces, that is where the trace of the animal, and the blue dots. One blue dot, that is one electrical potential from these cells. And what you see here is that there is a very regular pattern. And this is biology, so it shouldn't be so that you can fit in equilateral triangles into a pattern that is generated from biology. And remember how deep the cell is in the brain. So we did this together with Marianne Fyn and Torkel Hafting when Marianne was a PhD student in our lab. And we decided that this cell, which is sending information to the hippocampus, might function as a 2D ruler, a metric system in the brain. What is fascinating is that when you go from dorsal to ventral, then it's like if you draw this grid cell pattern on a balloon and you blow up, then there's an expansion when you go more and more ventral in this structure. That you see here. So cell 1, very dorsal, small fields close by, and then bigger fields further away, and then you have fields that are really big and quite far away. So why do I tell you this? Because I want to bring you back to hippocampus and ask, how can you come from these grid cells to a place cell? Is that possible? Because that is our hypothesis. Yes, you can. So if you align these grid cells on top of each other, you just do a normal linear summation. Then you see here in the middle, there's a bump, but at the edges, everything is cancelled out. And what do you get then? You get one bump, as we saw in the hippocampus. I have another question to ask too, and that is, how can this cell be so precise? It doesn't have eyes, it doesn't have ears, it doesn't have a nose, except on the animal, of course. So what type of information does this cell need in order to be so precise? It needs to know the direction of the animal, and it needs to know the speed, because when the animal is eating chocolate, it's stopping, it's running fast, and it's changing position all the time. So then we asked, are there such cells close to the grid cells? And Francesca Sargolini from Rome, she came to our lab, and she showed that there are some cells close to the grid cells that we call head direction cells. And they were not discovered by us, because they were discovered in another brain area by Jim Rank and Tauby. But she found them in entorhinal cortex, medial entorhinal cortex. So these cells work like this. So when the animal is going west, then it's pop, 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 pop. And then there's another cell. So it doesn't help if the animal is going only to west, but it has to point north in order to get this cell to be active. So this information is then given to the grid cell. But we also need information about the speed of the animal. And then the question this Argentinian postdoc had from Patagonia, Emilio Kropf, he asked, is there a speedometer in the brain feeding the grid cells with information? And he designed a car for the rats, because if you want to find cells that respond to the speed of the animal, you have to control the speed of the animal. And then if you can decide the speed of the car, then it's fine. But it's not completely fine, because the animal might fall asleep. So how can you keep the animal awake? Animal has to run. And that is why we have the Flintstone car here, to remind us that the animal is running. And in this way, Emilio could change the speed of the animal as much as he wanted. And I can show you one example of such an experiment that he did. So here the animal is running north, and here the animal is running south. These lines are just the individual laps that the animal is running, and these red dots, that is just where the animal or the cell is active. And you see when the speed is high, the cell is very, very active. Pop, 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 pop. And when the speed is slow, the cell is almost silent. And it doesn't matter whether the animal is driving north or south. The cell is signaling exactly the speed of the animal. And that is what we see also in 2D. So when the animal is just running, chasing chocolate in a box, like you have seen now so many times on these videos, So here we have 12 cells, and what you see here is that the pattern, the firing pattern is not interesting, but what is interesting is to see the correlation between the activity of the cell at the y-axis and the speed of the animal. And you see it's a beautiful linear summation. Okay, I have a message here, skip this version. I don't want an update on my computer now. So these two types of cells, they inform the grid cell about the speed of the animal and the direction. Then we asked the question, how is this process running? And we had two Chinese postdocs, Miao and Chichen. And we asked together with them, is it so that the GABAergic interneurons, are they involved in the precision of the firing of the grid cells? So to address that question, they ordered Cree mice that had a Cree activity on the parvalbumin cells and also the somatostatin. And they used this artificial receptor technique, the DREAD technique. So you just use a virus then that will go only to those cells that has the Cree tag in these mutant mice. And then you use an artificial ligand like the CNO. And then you can activate or inhibit only those cells that you are interested in. And that is exactly what Miao and Chichen did. And this is an example of 3 cells. No, one cell, sorry. So this is before they gave the artificial drug. This is when the drug is working, and this is when the drug is leaving the body. And you see that when there is drug in the brain of this mouse, this grid cell doesn't look like a grid cell anymore. And if you ask the grid score how much grid-like is the cells, then you see that when this drug is working, then we have much fewer grid cells in these mice than before. And the same thing happened with the speed. So you see here's the speed signal. When they have the drug, it's flat. When the drug is out of the body, then there's a speed signal. And that is summed up here. And you see that the speed score is very, very bad when this drug is working. And then, so what we showed here is that the parvalbumin cells are giving inhibition to the grid cells to keep the correct position of the fields. And the somatostatin, they did not have this effect, but they worked on different type of cells. So I'm sorry that I'm rushing because I have so much to tell you, and I know that I have limited time. So you have to shout at me if you think that I should move on or go a bit slower, or we have some questions at the end. We also want to compare the different maps in the hippocampus and the entorhinal cortex. And what is that very, very different, these maps? So the grid maps, they work together, all the grid cells from the same module. And it's like a mathematical paper that you bring with you. You might rotate it, you might shift it, but it's always the same. And that is illustrated here, that you go from room to room, and it's absolutely the same map. What is interesting, and this is not published yet, English postdoc Richard Garner studied the grid cells when the animal was sleeping. And then he asked, those cells that are active together when the animal is behaving, are they also active together during sleep? And that is what you see here with the cross-correlation when the animal is running and when it's deep sleep, slower sleep. So you see then they are correlated, but the cells that are not correlated during running, they are not correlated during sleeping either. So it's the same map even when the animal is sleeping. This girl, Charlotte Alme, a Norwegian PhD student in the lab, she worked with the hippocampus, and she tested the animals in 11 rooms. And she asked, is it so that the hippocampal map is similar to the entorhinal map, that it is the same map that is used over and over again, or does the hippocampus create new maps? And what is a map in this case? It's the activity of the different cells. So what she did was to put all the recordings from the different 11 exposures to the different rooms, put them on top of each other, and then she asked, are these correlated? And you see here's familiar one, and of course the same room is very correlated. But it's a lot of blue here, meaning that it's not correlated at all. That means that cells that are active in this room are not active at all in the other rooms. Except if you go back to the same room, then even after one exposure, the hippocampus is using the same map. So to just sum it up, it seems like we have so many uncorrelated maps in the hippocampus where you can store your memory. And that is different than from the grid cells that can rather give the metric to the spatial input. So then we have to rush on to ask the next question. Are there any indication of information in the entorhinal cortex telling the hippocampus about time? Then we got this absolutely fascinating and fantastic PhD student. He came to Norway from Washington when he was 18. So he was almost the same age as my daughter. And I said, no way, this is not good. He was so excellent, you can't imagine. So he said he wanted to study the lateral entorhinal cortex, and he was allowed to do that. So that is the sister structure of medial entorhinal cortex. So the grid cells are here, the lateral entorhinal cortex, that is where he put his electrodes. This poor guy, he came to Edvard and me, and he showed his results. And even though we loved this PhD student so much because he was so skilled, we said, this is not right. Because he had so unstable recordings that we said something must be wrong. And it took him 8 years and us to discuss this, and before he found out what was wrong with the data. What was wrong with the data was that time had been running in between. And this is illustrated in the experiment that he and Jørgen, another PhD student, or a postdoc in the lab, did. So that was in the same room. You can have this situation where the animal is running around in this box. You can have white walls, black walls, and you run the animal, put the animal in the box, put it back again, you clean between each, and that is exactly what happened. So this is the black box, white box, and then in between you have this pot situation. What happened with the cells is that each individual cell seemed to respond differently to this situation. So if you go to this cell said, I'm measuring how much time the animal is running in the box. So you see, if it's the black box, the firing rate is low and then increasing. Low, increasing, low, increasing. So it's measuring time or the trial time. This cell is doing something different. It's measuring the whole session, starting with high firing rate, and at the end of the last white box, there's almost no firing at all. And another cell is telling about what color the box had, and also how much time the rat was spending in each box. And then you have the same thing here with the wall color and the different sessions. So this was the confusing part. So then Albert came up with, what if we use the general linear model to ask what can tell us best, how can explain the variance in these data in the best way. So then he asked, what about the wall color? Does that explain any variance at all? And he compared the data from the lateral entorhinal cortex with structures that we were happy about, the CA3 from the hippocampus and the medial entorhinal cortex. And not much happened when it was only wall color. Then he asked about the position. And you see that the medial entorhinal cortex with the grid cells, they signal position best of these three structures. Then he asked about wall color and position, asking, is it a white box or black box? And where is the animal in the box? Then CA3 said, hey, this is my function. Then he came to lateral entorhinal cortex. And lateral entorhinal cortex was telling about time. So it was like a clock ticking, tick-tock, 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 and giving a tag to each episode that the animal experienced, each box. And this is just, when it was mixed, it didn't say much. So it seems like you have this running clock that can give you a tag to every episodic memory so that you can sort your episodic memories in the correct sequence. But as the spatial information is subjective, also time is subjective. And you know that. Maybe some of you think that this is such a slowly moving hour. And some of you think, oh, time is going so fast. And this happens also in the brain of these animals. Because when the animals were allowed to run in another task that was very repetitive, so they were asked to run in this H-shaped maze, up and down and up and down and up and down, and they got a reward, then time between each trial that they went to this apparatus was gone. They couldn't, these cells didn't tell much about that time. But now, these cells, exactly the same cells, told about how much, where in this apparatus is the animal. Because the experience is telling you about time. And this experience is so different from running in these different boxes. How much time do I have now? I have 10 minutes maybe, or less? 5? 15 minutes. You are an angel. Wow, then I can relax. Okay. So then the last question. Because when we have memories, we don't only know where it happened, when it happened, did it happen before lunch or did it happen after lunch? But we also have people in our memories, we have objects, and for the rats, it's easier for us if we ask this what question with objects. So we have this situation for the rat or for the mouse, that the animal is exposed to a Duplo or Lego tower or some toys that we put in. Because you remember the other boxes, they had only chocolate. Now we have chocolate and a queue. And Jim Knierim in the States, he asked this question first. So he had these different objects. He put them in the box, did exactly what we have been doing, giving the animal chocolate. And these white circles, that is 4 of these objects. And then these are different cells that respond to these objects. And when the cell is responding to the object, you know now the code that when there is color, there is activity. So then this cell is just, pop, 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 here's an object, pop, 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 here's an object, pop, 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 here's an object. Then, how many of you remember this guy? The time guy. He is also the object guy. So what he did was again to play. So you know, it's so important when you have questions that you really wonder how to address, that you can play. So we have people in our lab playing, trying out things, and suddenly they see something that is so exciting. So what Albert did was he was recording then in lateral entorhinal cortex, and he had this situation. It was this box. He had a Duplo tower here, and he had trained the rat for 14 days. And then he said, I have found some of these cells that Jim Kierman found that respond to the object. But I want to see what happens if I remove the object. So it is like you sit in a party and you wait for your best friend, and your best friend's chair is empty. Where is my best friend? So that happened to the rat. The rat was walking here in the object. It had been exposed to this object for 14 days. And this cell said, something is wrong. Look, it's firing, even though there is no object. So we decided to call these cells trace cells because they are the memories of what was there before. And then Albert started to play. So he moved the object to a new position. And you see that when he was moving, the trace was also exposed. So in this situation, he had moved so many objects, and this cell responded to all of these moved objects. There's nothing there. And he even cleaned the box with alcohol, with soap. There's nothing. And still these cells are saying, I have a memory for this place, there was an object. I have a memory for this place, there was an object. Then we have some other data that are not published. So Øyvind Høydal is the main person. He's a Norwegian PhD student in the lab. And he was working with mice, and he did what Albert did, give the mouse an object. He recorded now in medial entorhinal cortex, so he could record both grid cells and other types of speed cells, border cells, other types of cells. And then he asked, are there some cells that respond in a metric way to the object? So if this is an object, and you record from my medial entorhinal cortex, do I have some cells that respond in a metric way, how far I'm from this table, and also what direction I am? And he found that. So you see, this is an example of if there's no object, there's no firing. When the object is there, then you see a high firing rate close to the object, and different cells, they signal the different distance to the object. And different cells, they even signal the different direction to these objects. So I thought I had less time, so I removed those slides from my talk. But I can tell you that when Øyvind moved this object to a different position, this field moved after. Same distance, same direction. And different cells have different distance, different directions. So we think that these cells tell you where are you relative to the object. So it seems like objects are coded into our episodic memory. How much time now? 10 minutes? Thank you. Then I will end with something that is already published for some years ago, because I find it so intuitive. When you think about your episodic memory, and if you think about an odor, then it's so easy to retrieve a memory. Can you think about an odor that can give you a memory that you haven't been thinking about? Is there some paella or something that is smelling something? Oh, I'm back to Spain. So this was treated by Marcel Proust, of course, in his novel, talking about when he was a child, he was sitting with his aunt, and he got the tea, and he could dip the Madeleine cake into the tea, and it was this lovely taste. Then when he was grown up, he did the same, and he was sent back to his aunt. We studied this in the lab. How can you study this in the lab? Can you think about a task? You need an aunt, you need a Madeleine cake, you need a cup of tea. At least we have odors in the lab, and we have the rat Emma. And Emma, she is giving the task that when she is smelling chocolate, she should go to this corner, and then she is getting a reward. When she is smelling banana here, then she should go to this corner, and then she gets another reward. Do you think that Emma can do this task? It's quite complicated. Yeah? Should we see? That was chocolate. Chocolate. Banana. She's good. Chocolate. No. It doesn't help to cheat. And now she can't concentrate. So, you know, rats are like us. They give up sometimes. Banana? Yeah. And now she's back on track. And what this guy did, Kei Igarashi from Japan, was to record simultaneously from the hippocampus and the lateral entorhinal cortex when Emma and her friends solved this task. What was so exceptional with what he did was that he was able to record from the cells when Emma started to learn this, when she was completely naive, until she had learned the task. So he could follow the process in the brain when these two positions were coded and the positions were associated with the odors. And this is the last complicated slide, I will promise you, and it's very complicated. But we will just go through it, and then you get some idea. So this is recordings from the hippocampus, and these are recordings from the lateral entorhinal cortex. Each line here is one cell. Here. And another cell in lateral entorhinal cortex here. This first panels, that is when Emma is naive. She doesn't know the task at all. Or she has had some trials. And then this is when she is more skilled, and this is when she's very, very good, doing just a few errors. And this is when she's doing errors. Then you can see these colors that we have here. These colors are just the activity, the pop, 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 of the different cells. Some cells prefer the chocolate, red, and some cells prefer the banana. And this is where Emma is smelling the different odors. What I want you to see here is that here the maps are quite empty. There's not so much colors. But when Emma is skilled, you see there's a lot of red activity and a lot of green activity in both structures. So that means that in Emma's brain, she has developed a map that is a combination of the odor and the place. And what happens when Emma is doing an error? Her brain is empty. Have you ever had this feeling that your brain is empty? That happens. There's almost no color, no active cells telling Emma where to go. That's life. So we think that we have now discovered cells in the brain that code for where something happens, when it happened, and what happened. And then the hippocampus is fed this information, is receiving this information, so that the hippocampus can generate our episodic memory. There are some people who can't do this. And that is those people who have a lesion, a damage, when these cells are dead. This happens in some groups of Alzheimer's disease patients. It happens in also other people. So they have problems to encode new memories because these cells are dead. They have problems with spatial navigation. They even have problems to encode the sequence of events. This is the group, how it looked like 1 year ago, only Edvard's and my group. And I've told you about the people that have been involved. And of course, Edvard has been involved in everything. We have got a lot of support from our local university, the Kavli Foundation, the Research Council in Norway, the European framework, the ERC grants, and Louis Chantier, Kerber, Madame Bettencourt supported us, and so on. And then I would just like to end with another memory that I would like to share with you. I'm from the coast of Norway, and just enjoy. Thank you. Thank you so much. You have been an extraordinary audience. Thank you.
Thank you. I don't know if... Hello? Yes? No? Thank you. Thank you, Professor Moser, for your brilliant talk, and as you can see, highly inspiring lecture. And now the session is open for questions, so we encourage especially young people, students, young researchers, to ask questions to Professor Moser to use this unique opportunity. So, is there any question? There?
Can we get some light
Here?
in the room so
Yes,
we see you?
now we have light.
Good.
Okay, yeah. First of all, tusen takk is... Oh.
Wow.
It's obviously amazing to have you here, and I'm super excited. This might be a bit of a controversial question, but I assume most of the rats are male for like interference with hormones and so, but you were talking about Emma, and since spatial awareness is kind of like a gender issue, there's people saying, oh, you know, women have less of a spatial awareness and memory. So I was wondering if in the lab you've put in Emma and their counterpart Peter, let's say, and if there is any difference, or all brains, after all, are the same in the way that they work with these grid cells and space cells and head cells.
Thank you for asking this great question. So we had especially a postdoc from Britain, Ross Langston, and when she started in lab, she said, I'm only going to work with females because I'm going to prove that females have grid cells, border cells, head direction cells, and of course, they do.
Thank you. So, Lisette Menéndez de la Prida from Cajal Institute in Madrid. Thank you for your talk. It was really clear, and I'm very glad that you can come to deliver this new data in this fantastic venue. So my question is regarding Cajal. So Cajal identified the neuronal doctrine in which the self-identity is the building block of the brain. So my question is whether do you think that the functional categories are related with the cell type specificity?
What did you say? If the functional...
Grid cells or speed cells.
Oh yeah, how you get functions out of the network? Is that your question?
Whether they could be related with a cell type specific of the entorhinal cortex.
Oh, thank you for asking that question. So that was our dream when we found or discovered the grid cell, because if there would be a marker, a genetic marker or something with these grid cells saying that I'm a grid cell if you did only anatomy, that would have been fantastic. But we haven't been able to do that. So the closest we have come is this data that I showed you from the Chinese couple in the lab, where they showed that it seems like the stellate cells in layer 2 of the medial entorhinal cortex are receiving inhibition from the parvalbumin cells around. And then in order for these cells to be active, they have to get the information from the hippocampus. We have shown that by giving mucimol so that we inhibited the activity in the hippocampus, and the entorhinal stellate cells, they were left alone only with the inhibition that surrounded them, and another input, and that is the head direction. And what happened then was that before the grid cells disappeared, some of them became head direction cells. So that is telling us something about this network, and that is also why we thought this was so interesting to see that the interneurons stained with somatostatin, they are not involved in generating the grid cells. So we are closer to this. But what we also know is that the stellate cells are also border cells, and they could have other different functions. So it doesn't even, it's not enough to just say stellate cells are grid cells. So it's still a very puzzling question, but highly exciting. So we have some interesting ideas how to solve that. And we have some wonderful, wonderful postdocs working in the lab trying to solve this question. But that is science. You never know what you get.
Sorry, I'm not young. I'm not a physician, but a physicist. So I want to ask you, what do you think would happen in outer space? I mean, the pattern, the grid pattern in a different gravitational force, in a gravitational field, will be completely different. The man in the moon, or the man on the Mars will be different. We adapted to the new situation?
That's a wonderful question. So what happens when we go to space? Do the grid cells measure, give us the same metric? So there were some rats going out in space, but at that time they didn't know about the grid cells. They knew about the hippocampus and the place cells, but the experiments were so difficult. So it was just a short paragraph in Science telling rats have been in space. We don't know. But a related question to you is, what happens if the animal is flying? Even though it's not in outer space, but even to fly, it's a different information to you than if you count your steps. And there's a fantastic group in Israel, Nahum Ulanovsky, and he is studying bats. And when the bats are flying, he can record from the hippocampus or from the entorhinal cortex. And he has shown that the hippocampal place cell is now a sphere. And then the question is, and since you come from physics, how could you predict the grid cell, which should be a crystal? Should it be a perfect crystal? Could it be a squeezed crystal? How would these different fields be? And he's still struggling with that, because to get the coverage enough when the bat is flying, that has been difficult. But the rumor tells us that there is one 3D grid cell that looks like a crystal. But we're still waiting. Science needs a lot of people.
Well, thank you so much for your speech. It has been really interesting. So my question was, we don't see many female Nobel Prizes. So I would like to ask you, in your personal experience, have you ever faced any kind of discrimination against you for being a woman?
That's a very interesting question. So, you know, this little child that you saw, the little girl, she had a bigger brother, 10 years older, and I wanted to be him because he was so tough. So I never realized that I was different from the boys. I didn't think about it. But of course now I'm a grown-up. I'm soon an old woman. And I have realized that the expectations that you have towards a man and a woman is not always equal. And of course, if you want to grow curiosity and passion, if you don't expect people to do well, then it's more difficult. But for some people, it's fuel. I'm going to show them. So what I'm saying is that in Norway, we have been blessed with not so much discrimination, and not to myself. But I am aware that we have some challenges. And what is important is that we all love science, and we need diversity. We need different cultures. We need men and women, young and old. And we need to talk to each other to solve these big questions. And I think we would do that if we work together.
More questions? Here?
Hello. Thank you very much for your very nice talk. I'd like to ask, okay, we now know where the information that the hippocampus is analyzing comes from.
Entorhinal cortex.
Exactly. But where is information in the entorhinal cortex coming from?
That's a brilliant one. So, of course, we have students in our lab one Portuguese student and one or postdoc, and a postdoc from Holland, working on, for example, the question, where is the speed information coming from? And it's not published yet, but they have been tracing the brainstem and diagonal band, and it seems like this loop is very important for the speed information. Then you have information about the visuospatial environment, so parietal cortex is extremely important. You have the postrhinal important. And then, of course, the hippocampus is sending information back to the entorhinal cortex, telling the entorhinal cortex some important things. And there's odor information to the lateral entorhinal cortex. And what is so special is that, as I said, this is so far away from the direct sensory organs. So what we see in these structures is what the brain is generating from all this information that it's receiving. So that makes this even more interesting, because we go so deep in the brain and we are trying to understand how the brain is working, how it's coding, generating functions.
Lady, the third row.
Hi, first of all, thank you for your talk. It was really inspiring. Some surveys have shown that younger people nowadays are less interested in the STEM fields. So my question is, what would you tell them? What would you tell them? How would you convince young people to get into STEM fields and make science?
So I think that the advice I have to both you, the young ones, but also my generation, is to give opportunities for curious people to follow their passion. So if you have passion for some questions that are extremely important for you, you can't stop it. You just have to ask this question. And that is the question I got when we got the Nobel Prize. Why don't you, do you say this, sleep on your lobe? No, can you just relax? Don't do anything, because now you're done. Tick off, Nobel Prize. Of course not, because that was not the goal. The goal was to understand. And if you have this curiosity, like you had when you were a child, if you just let this curiosity grow in yourself, then you find out what is your question, what do you have passion for. And if it's not science, fine enough. But if it's science, welcome.
First of all, thank you for your talk. It was really amazing. So about the other cells, we humans have a underdeveloped vomeronasal nerve, unlike inferior mammals that, of course, like the rat, has a fully developed vomeronasal cells. I'm guessing it has connection with the how do you call the entorhinal cortex, sorry. So, I'm guessing that's the question. We should have a slightly undeveloped odor cells. I mean, like the rat. The rat could track the odor of this food, either it was a chocolate or a banana. It could track the odor and actually track it in a space. The rat wasn't looking right at it. As humans can't. So that's the question.
So are you asking about the vomeronasal organ, or are you asking about the experiment with Emma?
Yeah.
Okay, with Emma. So you have to remember that she got the chocolate and the banana odor in the same place. So it was this central place, and both odors were there. So in order for her to know where she should go, to right or to left, she had to make this association between the odor and the position. But what is interesting in your question is, if you did this test with me, maybe having not developed my olfactory system as well as Emma, could I do the task? I don't think so, but maybe. So, but what is important is that this is a redundant system. So this is back to your question, because into the hippocampus you get all kinds of information. So if you to generate, for example, the grid cell and the speed, you have the optical flow, you have the number of steps, you have also how fast you move. So if you remove the optical flow, you can still count the number of steps, and you know how fast you have gone. So it is a very redundant system. So you don't, if you don't have the ability to smell something, you can still do very fine. So that is my only response.
I think there's a question over here.
No.
Normally you don't, when you're in a room, normally you don't know where the real north is. So for the grid map, you need to fix a north. How do you fix it? Or
thank you for that question. It's a wonderful question. So I talked briefly about it when it came to time, that time is so subjective. And it's the same with the metric and the grid cells. So when I told you about these compass cells, I shouldn't call them compass because it's not connected to the magnetic north. So it is a map that is generated in us and in the animal. So when you come to a room for the first time, these cells just decide, this is north, this is east, and so on. And if you then go to a different room, having the same magnetic or different magnetic directions, then north suddenly can be there for this head direction cell, the same cell. So it's a system to help us to organize life. And those of you who know a tiny bit of philosophy, Kant, he said, you can't explore the world if you don't have this faculty before you start to explore. So it's just a help for us to understand the world, the mission of the tiny girl.
There's a question over here.
Hi, and thank you very much for your talk. It was incredible. I would like to know, you talk about the odors and the relationship with the memory, and I want to know if the sounds have the same effect, the music or something like that could have the same effect, could be related to the memory?
So absolutely, and even in patients with memory problems, some of their problems is to find a good retrieval cue. And then you see with really severe Alzheimer's disease that if you play some music that they know, it seems like it can circumvent entorhinal cortex and the hippocampus that is damaged and then go to a storage out in the cortex. So the challenge for the memory is interference, that you start to mix memories, and also to find the retrieval cue. And that is why odors are so fantastic. Because, so I was at one conference, and then John Aggleton told me about a museum in New York. And that's a Viking museum, and you know Norwegians, we are Vikings. So he said, at this museum, they had the Viking exhibition, and they smelled terribly, these Vikings. And you could buy these terrible smells in the souvenir shop at the museum. So John, he went there and he bought these odors, and he met people that hadn't been to this museum for 20 years. And he exposed these people from different odors, and then he asked, what do you think about when you smell it? Oh, this is the York Museum. So, you know, odors are, even pleasant odors are very, very good retrieval cues. So you just have to find out. And that is also useful when you have to memorize things that you just have to memorize that you don't understand. And then you can use this old-fashioned technique with the memory palace, which is very useful. Then you use space as a retrieval cue. So you go from room to room and then pick up your memories when you mentally travel from room to room.
Well, we have time for only 2 questions. There was one question over there.
And then one over there.
There were before, sorry. Let's see. There. Here, in the middle. No, levanta más la mano, que si no, no te ven. Yeah.
Thank you. So I think that I understood that many of the graphics that you showed us were representing the activity of just one neuron. And I was just really curious if you could tell us how the sensors work and are showing just the response of one neuron.
Oh yeah, thank you for that question. So what we do is that we have ultra-thin electrodes. So it's a quarter of a hair. That is one. Then we twist 4 of them together, and we cut them with a golden scissor so that these 4 are so close, like this. Then we put the animal down with morphine and isoforane, and we open a tiny bit in the skull, and then we can insert these hair-thin electrodes into the brain close to where we want to go. But then when the animal is awake and happy, running around, we can turn these electrodes down without the animal can feel anything. And then we can listen, and we can test the animal. And then finally, we hear a response, pop, 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 pop. Because we have a camera above the animal when the animal is running, so we can track the behavior, and we can track the signals. And what we do is just to correlate 2 and 2 electrodes and ask, how does the cell look like on this? So this is extracellular recordings. And in this way, we have these clouds of activity that are separated because there is a distance between the electrode and the different cells. And in this way, you can follow these clouds for days and weeks. And even I followed some of my cells for half a year. And that's possible because you know the signature for each cell. And you magnify the small electrical potentials 10,000 times so that you can see it on an oscilloscope and you can listen.
So we have time for one last question at the back there.
Hi, thank you for your talk. I was wondering about the encoding process. When you study those animals and you study these grid cells and place cells, about the molecular process of how do they encode, if you have performed some experiments, for example, I think about the Sina Jocelyn's papers about the entorhinal cortex and how do they increase CREB levels on those cells, and they see that they are more prone to encode this new information. If you have to think about this process could be happening at your model, because they study contextual fear memories, but this is another kind of memory, but is very related. And also how the neurogenesis could also interfere in throughout the time, forgetting those memories that you are studying. Thank you.
Thank you for that question. So I can't answer you so much because we have a postdoc in the lab who is applying for a European Research Council grant. He's the most fantastic postdoc from Italy. And so I can't tell his proposal, but he's going to study exactly this. How do you set up these networks during development? How can you select the cells that will become place cells that are active in these different rooms? How is the brain dealing with this? So I can say that there will be answers to those questions that you have, but I can't tell you how he's doing it. I'm sorry.
Thank you very much.
Ahora ya tienen que pasar. Nosotros ya nos vamos, ¿no?
Thank you. Oh, nice to meet you. Oh, what an honor to meet you.
Thank you so much, Professor Moser, for your special, memorable lecture. And now I would like to send some special words for our students. La Facultad de Medicina quiere que este día sea memorable para todos ustedes, que lo guarden en su memoria, el comienzo del curso académico 2018-2019. No voy a repetir la contribución gigantesca detrás de la que hay un esfuerzo titánico de la profesora Moser como investigadora, que de hecho les permite a ustedes saber dónde están en este momento y su lugar cuál es, y ser conscientes de eso, ¿no? Y tener su carta de navegación, ¿no?, en el entorno próximo. También quiero destacar que es del selecto grupo de mujeres ganadoras de Nobel, que es muy limitado y muy restringido. Lo mismo que lo es en su momento cuando lo ganó el matrimonio Moser, ¿no? Hay pocos matrimonios. Matrimonio Curie, matrimonio Carl-Gori, sí, el del ciclo de Cori, ¿no?, de biología, ¿no? Pero más allá de que los conocimientos, el testimonio de hoy es ejemplificar que el esfuerzo en la investigación merece la pena, que la investigación en medicina es arrebatadora, y que por lo tanto ustedes están en el centro del conocimiento y con las personas que tienen ese conocimiento, y que contribuyen a la historia de la medicina, que contribuyen a la historia de la ciencia. Y esto es algo como decir que contribuyen a la historia de la humanidad, ¿no? Thank you again, Professor Moser, for your contribution to the medicine and physiology, your contribution to the science history and the human history.
Thank you.
A propuesta de la Facultad de Medicina, la Academia Médico-Quirúrgica Española tiene un mensaje que trasladar a la profesora Moser y le cedo la palabra al profesor Ortiz Quintana, que es el presidente de la misma.
Doctora Moser, vicedecanos, estudiantes, autoridades, just 2 words in English to understand you, what I want to need. I speak on behalf of the Spanish Academy of Medicine and Surgery, and this event for us is a great honor. We translate here the result of the Committee of Governors of this Academy when the President and myself proposed you as a honor member of our Academy. We have only 6 honor members in our Academy, and of course you are the youngest of all of them. It's very important, all of us say yes. There's one debate, but no discussion. It's very surprising. It's the first time that we no discuss about one proposal with a new member, honor or no honor, and number academic, nominal academic. So I will read it very shortly in Spanish because it's a Spanish Academy, and I think I have to read this 4 or 5 lines, it's very shortly, in Spanish, and when I finish, I'll give you the certified with recognize you as an honor academy, and will hang in your neck our medal. And I hope, for us, it's a great honor, and I hope that for you, at least, what a small honor.
It's a fantastic honor.
Junta de Gobierno de la Academia Médico-Quirúrgica Española, celebrada el 27 de julio del 2018 con la presencia de todos sus miembros. Punto 3. Nombramiento de nuevos académicos. Lectura de los acuerdos tomados en base al capítulo 2, artículo 2, que regulan el nombramiento de nuevos académicos que deben ser propuestos por mayoría absoluta de los miembros de la Junta de Gobierno de la Academia. El presidente propone el nombramiento de la doctora May-Britt Moser como académica de honor por sus méritos excepcionales basados en los descubrimientos de células que constituyen un sistema de posicionamiento en el cerebro, motivo por el que le fue concedido el Premio Nobel de Fisiología en 2014. Todos los asistentes manifiestan una opinión favorable a la propuesta del presidente, por lo que se aprueba por unanimidad. La entrega del diploma y de la venera académica que la acreditan como tal se efectuará durante el acto previsto para el 26 de septiembre en la Facultad de Medicina de la Universidad Complutense. Ahora les voy a hacer entrega del diploma académico. I think it's very nice.
Thank you so much. Thank you.
Now I will try to hang this medal on your neck.
For me?
It's for you.
Wow. Thank you so much. Thank you. Thank you again. Thank you.
Not necessary, but...
At least, so now I have to admit I'm a bit tired, I'm very sweaty, and I don't know what to say, but I know one word that is important in this situation. I'm extremely honored to be an honorary member of your academy, and I would just like to express that I'm very grateful. Thank you so much.
Thank you very much. For the medal.
Oh, thank you. So beautiful. Thank you. So then I can go down. Okay, thank you so much.
Bueno, hola, muy buenas a todos. Buenos días, muchas gracias por estar aquí. Mi nombre es Eduardo Recoder, soy el presidente de AstraZeneca en España. Es un gran honor poder teneros a todos aquí en este Nobel Prize Inspiration Initiative que desde la Fundación AstraZeneca traemos a España por segunda vez. Tuve la oportunidad de iniciar este tipo de iniciativas en Brasil hace ya unos años, cuando estuve trabajando allí. Me parecía que era una cosa impresionante y una oportunidad fantástica para atraer pues, a laureados, ¿no?, como la profesora Moser, para que os pueda transmitir, ¿no?, la pasión por la ciencia, ¿no?, y animaros a ello. Permitirme también, entonces, bueno, en primer lugar, que mis palabras sean de agradecimiento a la excelentísima señora doctora May-Britt Moser. Thank you very much for sharing with us not only your work, but also your passion, right? So I think that is really the message. We had the opportunity to talk about it yesterday night, right? And this is what is really helping younger scientists to get inspired, no? about the passion that people like the professor is showing in what she's doing. Y es un espejo, ¿no?, donde mirarnos a la hora de continuar desarrollando investigaciones que algún día puedan transformar la vida de millones de personas. De alguna forma, ese es el objetivo común que tenemos, ¿no?, desde la Fundación AstraZeneca, desde lo que es también la industria farmacéutica, conseguir que esa ciencia y esa innovación termine redundando en la vida de los pacientes. Quisiera dar las gracias también, como no, al señor don Carlos Andradas, rector de la Universidad Complutense de Madrid, al señor don Javier Arias, decano de la Facultad de Medicina, al señor don Jesús Millán, vicedecano de Relaciones Institucionales e Innovación docente, a la señora doña Elena María Vara, vicedecana de Estudiantes, y a doña Maribel Colado, secretaria académica. La verdad es que sin la colaboración de vosotros esto hubiera sido imposible. Da muchísimo trabajo, ¿no?, preparar todo esto, coordinar todo, agendas, logística. Y fijaros, más de 1.300 personas os habéis interesado por esta oportunidad. Aquí caben aproximadamente 800 personas. El resto están en otras salas, han tenido la oportunidad también de asistir a la conferencia. Ayer, cuando hablaba también con la profesora sobre eso, ¿no?, sobre el nivel de asistencia que íbamos a tener, estaba preocupada. Bueno, ¿y qué pasará con los que no quepan, ¿no? Me han dicho que caben más o menos 1.000 personas. Bueno, pues efectivamente, ¿no?, la organización de la universidad pues, ha permitido que todo el mundo en otras salas e incluso online pues, tenga la oportunidad de asistir. Así que, de nuevo, muchísimas gracias por la preparación y por hacerlo posible. Yo esta mañana hemos llegado un poco antes, ¿no?, hemos bajado a la cafetería a tomar un café y le decía a mis compañeros qué recuerdos aquellos, ¿no? Yo también estuve en la facultad, yo soy farmacéutico, estudié la carrera de farmacia y de una forma u otra, pues, bueno, pues siempre he estado vinculado a la ciencia, ¿no? Al final, pues, aposté por la industria farmacéutica, a crecer en la industria farmacéutica. Hoy tengo la oportunidad de dirigir, ¿no?, pues una compañía aquí en España. Pero lo más importante es la oportunidad de poder estar vinculado a la ciencia. Sabéis que la ciencia no entiende ni de razas, ni de géneros, ni de edad, lo habéis podido comprobar, pero también sabéis que es una carrera de fondo, ¿no? Es una carrera que requiere pues, de exigencia, de constancia, de inconformismo y de mucha pasión. Habrá momentos que lo queráis abandonar, ¿no? Y yo os digo, no lo hagáis. O sea, volver a pensar en esa pasión, ¿no?, en la foto de la niña que mostraba la profesora, pues si tenéis esa foto vosotros, pues hacerlo realmente una realidad, luchando y con vuestro esfuerzo, ¿no? Y si hay alguien que necesitamos de alguna forma para el futuro de la ciencia, el futuro de la medicina, de la farmacia, de la biología, pues sois vosotros, el talento más joven que aporta ideas disruptivas, creatividad, pasión. Vosotros sois el motor que nos impulsa a cruzar la meta y a mejorar la vida de las personas. Por eso, mirar también hacia atrás, preguntaros por qué sois médicos o por qué estáis queriendo ser farmacéuticos, biólogos, químicos, por qué sois o queréis ser investigadores. Mirar hacia atrás, recordar a la doctora y profesora Moser, que con su trabajo ha marcado un antes y un después en la historia de la ciencia. Estáis empezando esa aventura, seguid dando esos pasos. Y nosotros, las empresas, las instituciones, las universidades, los centros de investigación, os tenemos que apoyar. Juntos debemos daros la oportunidad que necesitáis para vivir la aventura, que sea vuestra aventura, que seguro será maravillosa. Así que muchas gracias a todos de nuevo y continuemos dando vida a la ciencia. Gracias.